Hello, thanks for coming out, like she said. My name is Philip Fisher-Ogden. I'm a director of engineering at Netflix. I'm going to talk to you about Don't Fear the Rise of the Machines, or why you can't scale ops by copying John Connor. Let me start out with a familiar story. Let's say you had a long day at work, you go home, you're ready to binge watch on Netflix Terminator 1, 2, 3, 4, maybe even Terminator Chronicles. You're ready for an all-nighter. You're set in your ways. You sit down, you start watching, you get paged. Something's going on at work, there's a fire. So you jump on, you're looking at, did we run out of memory? Did we run out of CPU? Was there a network problem? What happened? After minutes, maybe even hours of investigation, you figure out it's probably this. You start twiddling a few knobs. Lo and behold, things are restored to working. So you binge watch your Terminator series, you go to bed, 3 in the morning, you get paged again. You try looking at the same things that it was the first time. It ends up being something entirely new. Again, minutes to hours later, you twiddle a few more knobs, things are working, you can go back to sleep. But by that point, you're pretty worn. I've seen this happen at Netflix when we had 10 servers 7 years ago to a few weeks ago when we had tens of thousands of servers. We have the process that looks a little bit like this. A failure happens, something in our systems help detect it. Maybe even humans are looking at a TV on the wall, they detect it. We get a bunch of folks engaged, we triage it. We end up with this little knob twiddling. A group of folks change a few settings, and all of a sudden, the recovery. So the next day, we take a look at why did it fail? What was the gap? What did we miss? And we add more metrics. We add more logging. We add more alerts so that we can email people. We update our dashboard so it's easier to see what failed, what went wrong. But all of this is focused on the person. It's focused on getting a person engaged to debug what the heck's going on. The problem with that is that machines and people are not the same. Machines have their own strengths and people have different strengths. So if I think about a machine, I could describe it as its fast execution of pre-programmed logic on a large set of data. And if that's the problem it's trying to solve, it does it much faster than any of us can do it. If you think about a human, we have slow execution relative to machines. We can do higher order thinking, though. We can take in a limited amount of data and do a very complex analysis of it. But the way that we do incidents and improvements today doesn't match this, at least certainly for the teams I've seen at Netflix. Why are we stuck in the cycle? Why do we keep putting the human in the center of things? I say it's fear. We've seen too many Terminator movies. We're afraid if we let the machines take over, we'll end up in a world where none of us are left anymore except for John Connor, and he has to lead the resistance to defeat Skynet. So I say let's try to get over that fear. We can have a much better world if we do that. The future I'd like us to see into starts with the machines and ends with the humans. The machines do what they do great. As soon as a problem is detected, the machines start deciding, can they shed load? Can they gracefully degrade? Can they engage fallbacks? They gather forensic data without even being asked to do it. They can look at queues, locks, memory on our machines. They can correlate signals. So by the time a human gets in the mix, you're given a set of information that says, this is what's happening, this is what it might be due to, and I've taken these actions, I being the machine, have taken these actions to try to correct it. So that you can possibly say, all right, everything works, or maybe you need to do a little bit of decisions on further actions. But you can operate at the machine speed rather than the human speed. So how do we get there? I think we can start with 4 things. Many of us will have run books that says, if this happens, do X, Y, and Z. Let's start automating those. If you can write it, you can code it. The next thing is implementing resilience patterns. Things like retries, fallbacks, throttling, bulkhead, circuit breakers. Not all of our systems have these in every place, but by putting them in place, our systems can automatically start responding to problems. The next thing is require automated response actions for alerts. I don't even practice myself, but I'm putting out this as we should put this as a high bar. If you're going to write an alert, don't allow it to be just emailing you. Say there's some action you have to correlate. You have to have the alert take. My team, for example, got 40 alerts yesterday over the course of the day, and it ended up being one bad node in our Cassandra cluster that an engineer on my team got paged, and after probably the 13th alert said, okay, I'll look into this, and ended up finding, okay, it's one bad node. That's something that can easily be automated. He doesn't need to get paged, and I don't need to get 40 emails about that. I need to get one that says, I think it was this bad node, I took action, review just in case the machine missed anything. The last thing I think is we need to invest in resilience as a product feature. As Ben Traynor said last year, if the product doesn't work, it doesn't matter what the features are. So each of us, let's step up and say, we need to add the new bells and whistles to our products, but we also need to make sure that stuff works. So let's spend some time with software engineering investing in that and putting that as a priority. To close with, I say we should stop trying to copy John Connor. There's no Skynet that's going to rule the world. There's no one-person-led resistance. Let's let the machines do what they do best. we'll sleep better at night. We'll be able to have pages that can be ignored or looked at a little bit after. We can binge watch our Terminator series, and the world will be a much better place. Thank you. So like she was mentioning, we'll do questions for a few minutes. Go up to the mic if you wouldn't mind. And I'll go back to this slide.
What are the things that the machines should respond to and what the engineers should respond to? We created something in my teams at Facebook, but I'm just wondering whether you have any models on that.
Yeah, so I can give you a few examples that we've done at Netflix. One of the ones we worked on before last Christmas and New Year's, which is one of our big seasons of the year, is doing outlier analysis to figure out nodes that are out of bounds of normal performance. And the machine would do that automatically and then decide these are some likely candidates for bad servers. And what we currently do is we terminate it, which isn't great if there was an actual root cause that was persistent rather than a transient root cause. And so we're thinking next step would be do the forensic data. So if you're doing heap dumps, you're doing looking at the network interactions, you're looking at those things, automating that. So we do have a few examples of that.
Yeah, just like the model we came up with is like whatever is a machine level metric, a computer should respond to, and whatever is like a service level metric, which is kind of affecting larger scope things, then we always consider machine level stuff as software bugs. If automation didn't do it, it should, so we should fix it. And if it's a service affecting issue, then it's a human that should look at it because it requires a little more.
That's a good way, yeah. So you say this is too complex for machine. It's a good way of looking at it, yeah. Andrew.
How do you think about, I'm thinking of this real time, how do you think about ensuring that you actually go back and loop around and fix the root cause analysis things versus like just automating all the run books and then not actually improving the system? Like what's the point at which you say, okay, this is too automated, like we actually have root cause we have to fix?
Yeah, it's a great question. So how do you know which stuff you're ignoring that's going to turn into maybe the Ebola virus and end up wiping out all of your server farms versus something that is just acute, like a flu, and you can solve easily? We don't have a great solution. So we've got different philosophies. We've got me, where I'm coming from, pushing on let's try to have the automated action be taken first, and then see which things that it isn't able to solve. And I think that we've got other folks in the company that are saying, let's have humans get engaged more on it because most of the problems we see are too complex. So we don't have a great solution, but we're thinking about that. Yeah.
Hi, so some of what you described is in some circles called the leftover principle, that the computer should do as much as it can, what's left over can be done by humans. And this creates a terrible situation because it builds a system that's so complex that the only work left to do is done by humans who aren't smart enough to, or now you have to hire at such a high level that it's very difficult to find people. Also, when there is a problem, problems are so rare that people are out of practice. So I would like to recommend a different philosophy, which is the robotic arm philosophy, which is rather than the leftover principle, we should cooperate with the robots, and the robots should be our assistants that take care of the little things, but let us do the work, like having a really powerful robotic arm. And that way, when the robots do take over, it's a cooperative thing, we're not their slaves.
Absolutely, I love that, yeah.
And I think it requires us to build our software very differently, because the leftover principle is a trap that we fall into if we don't plan out our engineering.
Yeah, I love it. Yeah, so the robotic arm being assistance rather than replacement is what you're saying.
Right.
Excellent. Good point. Let's do maybe one last question. So,
how do you test out automation in canary nodes or similar test and production strategies?
Relative to resilience or relative to other stuff?
Relative to resilience.
Okay. So certainly for the outlier detection, one of the things we did was we ran it for 3 or 4 weeks, and then we did basically supervised learning where humans getting engaged and saying yes, no, for this is actually an outlier. And that gave us the confidence that we could run it without the human yes, no. For canary analysis, that's a lot more complex. But talk with me or Coburn, the man in the gray, afterwards. We can definitely chat about that. Thank you, everybody.
Okay, sweet. Hello, I'm Drew Michelle. I'm an SRE at Spotify. I'm going to be talking to you about how we manage our bare metal fleet of servers. So I want to take a step back into the past. A few years ago, there was an enormous amount of manual work that was needed to be done in order to spin up a machine. And this is an example of a dev requesting 6 machines and a couple of different data centers for a new ad tracking service. So I want to talk about the results of this manual work. So it was painful. It was painful for the developers, and it was painful for operations. For the developers, they would pretty much submit a Jira request and wait, right? It was kind of a black hole to them for when hardware would become available. For operations, of course, this was a queue, and it was manually consumed. So again, that's kind of painful, boring work, perfect example for something that should be automated. And we also found that when developers are waiting for hardware, that the quality of the software suffers, right? So the developers try to do things clever with their code to wait for the lack of hardware. And this obviously doesn't scale. So for the number of developers, squads, and servers we have. And to put that into perspective, we now have, Spotify has 1,500 employees. We have roughly 9,000 machines in 4 different data centers. And we have 60 million MAUs. So we all know automation trumps doing manual work, right? So hopefully you have no one in your organization telling you, back in my day, we provisioned machines by hand, right? No one wants that. So we want to automate all the things. So the solution we came up with was Cortana. Now, if you have any questions about the name, you can ask my product owner sitting right there. It's really because I'm a big fan of Halo. So Cortana this is multiple iterations later, but it was our solution to doing self-service provisioning and what we call the triple R, which is to let a developer reinstall the machine, which is essentially to reimage it, reboot it, do any power action, or to recycle it, which returns it back to the available hardware pool. So it lets the dev manage the complete life cycle of the server. So here's a screenshot of what it looks like to request hardware. I guess you can't really see, but very simple. You select what hardware type you want, where you want it. There is something that says role there, which maps back to puppet classes that get applied to the machine and the quantity. And the developer clicks submit. And within 10 minutes, they get their bare metal machines. So they no longer have to wait. And here's another screenshot of what it looks like to manage the machine. So if you want to manage an individual instance, you could just come here, find it, you can reboot it, recycle it, or reinstall it. So this ties into something we call ops and squads at Spotify. And this is for squads to take on operational responsibility for the service. They own the pipeline end to end. And in order to succeed with this, they need a high level of autonomy. So I talked about server management, but we also have this for self-merges of DNS data and for puppet changes. So in conclusion, right, everything is awesome. Get ops out of the way of doing developer work, out of the way of developers. Create services, products instead for them to use, CLI tools, any kind of automation, and have your devs focus on releasing features instead. Yesterday during the Facebook keynote, I think Petro mentioned how many man hours were saved by their automation. I don't have that number. I plan on getting that when I get back to the office, but I don't think it's close to 27,000 hours a day. Much lower than that, but thank you. Questions?
So if devs can just spin up machines willy-nilly, how do you do capacity planning?
Capacity planning is very interesting. We have kind of a monolithic spreadsheet to do that takes in all these inputs, but essentially just throw hardware at the problem.
Hi, great talk. So I'm just wondering, how do you manage like special requests by devs, like something that falls outside of your normal standard build, or you just have like a wide range of builds? Like, what are you doing to provide
Yeah, we have a couple different hardware types that kind of put things in like perspective for developers. Like if you need a database machine with lots of I/O, we have that high CPU, high memory, database or storage. So we try to do it that way. But if a developer has like a special request, we work with them.
Okay, so you just basically keep a certain like float of spares for each type of hardware class.
Yeah, we try to keep a minimum of like 30% capacity across all our data centers.
Awesome, thanks.
Yep.
How do you deal with repairs? So, like, if a developer has a bad disk, does it go, like, we have a very similar model. Do you just recycle it and then repairs happen? Or is it like 4 hours instead of 3, really?
Well, so if it's broken now, the developer can alert us, open up a Jira, and we'll take a look at the machine for them. We have plans to do this all inside of our Pixie image for to actually like detect that the hardware is broken. So they would click recycle, we would automatically detect that there was a hardware problem and mark it as broken and get that out to our DC ops team.
Okay, yeah, I was just curious, like, why even have the Jira ticket? Why not just use the Amazon model and just say throw it away and like it's somebody else's problem?
Yeah, and it's kind of like a half our problem now to get it fixed since it is a physical machine, and I guess most of them are under warranty, so we can get them fixed. Can't just throw them away.
So the first question is Linux only?
Yeah.
Yeah, okay, that makes it easy. It's like we do Linux, we do Windows, we do Mac. We have something similar. What are you using underneath? Is it just Pixie Boot, Kickstart, whatever, or are you using OpenStack?
So I think central to this is our CMDB. We call it ServerDB. We wrote it in-house, and that's like the inventory of all the servers, and then we just wrap a bunch of stuff around that. But yeah, it's pretty much, we chain load iPixie, and we have a Pixie image that has all the logic for installs in it.
Last question, do you have like a RESTful API sitting in front of this, or is it all driven through the GUI?
No, so there's an option to use an API. Spotify open source something called CRT auth, which you use public and private key pairs, so you can use that to interface with the API.
Cool, thanks.
Hi, thanks. So I think the focus of this was about devs provisioning for their specific use to kind of hash out code changes, right? Do you guys use this to scale out as well, or is that process different?
It's used to scale out.
So if I was a developer or a PM or whatever, and I said, okay, I needed 500 boxes in each DC or whatever, and you didn't have that capacity, what do you fall back to?
So if someone's requesting 500 machines, hopefully they came and talked to us before needing all that capacity. Yeah.
Okay.
Hopefully they come and talk to us. Yeah, it's a layer.
So I had a question. Do you see this scaling in the future? Are you guys still going to be handing out physical boxes to devs? Or are you going to look to other solutions around virtualization or containers, et cetera?
No, we're looking at scheduling. So we have an open source project called Helios, which is a wrapper kind of around Docker. So I think we see that as the future.
Okay.
Yep. Thanks.
Hello. Get my stuff together. Okay. My name's Ben O'Connor. I'm here from TripAdvisor, and I'm going to talk about how we built a 0.5 petabyte NAS system using commodity iSCSI storage backends and open source software. So the origin of the project is that this is a system that we use to store nearline application web logs for the system. They're all aged off to S3 after about 5 months. In many ways, this is just a legacy system because all of our logs also go into Hadoop for other analysis. The old system that this was running on was sort of an octopus of direct attached SATA chassis off of single systems and was taking up multiple racks and falling apart and getting old. At TripAdvisor, our motto is, at least operationally, our motto is speed wins. So we had about a month to completely replace the old system and build something new. The requirements, size requirement was 250 terabytes day one. Growth to today was about 500 terabytes. Even though our retention period is fixed, the log growth at TripAdvisor is pretty linear, so we're at 500 terabytes today. Big requirement was that as we expanded it, we needed the bits to be rebalanced to the new LUNs, and so old LUNs could be removed, new LUNs added, and all the stripes could be rebalanced for performance. Let's see. Other requirement was that it had to be cheap. We had a pretty low budget, and as I said, this is sort of a legacy system. And as a company, we don't really like black box vendor provided solutions, so we decided this was a good chance to build something on our own. In terms of reliability, this is a tier 2 system, which means it's not super business critical. Obviously, we don't want any data loss, and there's some analytics that run off of this every day. But having it go down for a few hours occasionally, not the end of the world. Let's see. So how do we implement it? We used some cheap, high-density iSCSI shelves in the back end, 65 terabyte drives each, 10 gigabit base T copper on the back end. Copper saves a lot of cost and effort over using multi-mode fiber with SFPs and fiber switching and all that stuff. Saved a lot of money. The NAS heads on top are commodity Linux servers, a lot of RAM for file storage buffering. They're active standby, so only one of them exports the actual file system, NFS and rsync at a time, and only one of them mounts the underlying iSCSI file system. We decided to use BetterFS for the file system here. We figured at the time we built this, which is about a year and a half, 2 years ago, it's mature enough for this project, and that this is a good place in the company for an exploratory project, sort of testing out something new. It fit the requirement to allow rebalancing to new LUNs. As we add new LUNs, we can run a BetterFS rebalance to rebalance the bits across them. And as I said, it was reliable enough. It's business critical, but only tier 2. Let's see. Okay, so some of the challenges we run across. In practice, defragmenting or rebalancing a single 29 terabyte BTRFS LUN would take about a month because that's a lot of data. Each of our chassis has 6 LUNs in it, so the operation to rebuild the chassis or to add a new chassis to do a full rebalance of that takes about 6 months to move 190 to 200 terabytes of data. Luckily, as I said before, all of our data ages off after 6 months anyway. So if we were to add a new chassis or remove one, we'd just wait the 5 months for all the data to be deleted and remade, so it would be rebalanced. So that sort of saved us there. Unfortunately, there's also some performance issues with BetterFS with some use cases. If you got complex directory structures or directories with a lot of little files in it, it can tend to grind to a halt, especially if you're not rebalancing frequently and you're not defragmenting frequently. And as I said before, the rebalance operation takes several months, so we generally don't do that. The way we saved ourselves there was to keep the capacity under 75%, and we actually made a separate file system on the same system that uses XFS, but is much smaller, and that's where the weird stuff goes with lots of little files and complex structures. Early on, we had some stability issues with lockups and some performance-related bugs. It's much better now that now that BTRFS is more mature, and we're keeping up with modern kernels. Right now, we're actually running on 3.18, which saved us a lot of performance problems. So overall, the verdict, operationally, it requires a lot of special knowledge. iSCSI networking, BTRFS tuning, Linux failover, stuff that we wouldn't have had to worry about if we just went to NetApp or EMC and bought a big, ugly thing ourselves. And when we run into problems, we're sort of on our own. There's not a lot of similar deployments out there in the wild that are this big for BTRFS. But we'd like to compare notes if anybody else out there has something similar or is thinking of doing something similar. Reliability has been good enough. Like I said early on, there were some performance and bug-related outages. there were some problems when we got capacity up over 80% or when our metadata space filled up and everything locked up. But those are things that we sort of learned from, and things are getting better now. At the same time, as performance gets better, more people want to use it. So on the top end, we've got more pressure on it with more NFS clients and more rsync clients trying to use it. And cost-wise, it was built for less than half the cost of a vendor-supplied solution. And it's still, even at the scale we have it today, which is up over 500 terabytes, it's still much cheaper than anything we would have bought on our own. So next steps for here is we want to fine-tune the failover between the NAS head nodes, split it up maybe into a few smaller volumes because the big volume is just becoming unmanageable. Restrict who uses it on the top to sort of lower the performance requirements. And we had to disable copy on write for the file system, also for performance issues, but we hope to re-enable that soon. And that's it. Any questions?
Hi, I get a question. Why iSCSI and not something that is distributed like Ceph, for example?
So Ceph, we sort of did a bake-off of this in Ceph at the same time. And in order to get this amount of size in Ceph, it would have required enough nodes that it would have been much more expensive. And also there's not so much a write performance hit with this as there is with Ceph because you're writing the data multiple times across the back end of Ceph. So this saved us a little bit of performance. We're building a new storage system actually next month that uses Ceph for VM images, and that works really great for that. But when you try to then turn Ceph and you put the Ceph POSIX file system on top of it and then you export it NFS, it's sort of a little bit clunky.
So given what you learned using BetterFS, would you still use it again?
I think we would definitely still use it, but we would be very careful to only put certain types of the big logs on it, and we would have split it off into multiple ones beforehand. What we're probably going to do within the next 6 months is split it off by month so that there's the current month of logs and there's the month before, so each actual file system isn't more than 100 terabytes.
You mentioned that this solution saved you at least 50% compared to an external solution. I was just wondering, did that value for your cost include your engineering, ops, and development time?
It did not, but up until today, all of the, at least my boss says, all of the ops and developing time that we've used to build this has been valuable because it's stuff that we've learned and applied to other places in the company. There's after this, there's two other BetterFS deployments that we've done, and this is the same iSCSI backend that once we learn how to build it, we're using it other places in the company too. So useful.
Thank you very much.
You might have covered it, but do you guys have sort of inherent compression on this? If it's log data, are you storing things compressed or having the file system do it?
It's already compressed by the time it gets to the.
Okay.
Hi, we've actually tried using BetterFS a few times in production as well, and we found we just had to constantly jump to newer and newer kernel versions. So that's, I see by your nodding, that's a thing that you guys.
That is what we do. Yes.
Okay.
Since about 3.14, 3.15, it's been a little bit better, but we still, every 3 or 4 months, we'll get the newest version. All right. Thank you.
Good morning. My name is Chris Namura. I'm an SRE at AOL. Yes, AOL still exists. So what I wanted to do with this talk was to share a couple of tips and tricks, because that's one of the reasons that I love coming to conventions. And I also didn't see much about security or benchmarking or performance testing. And even though this isn't Black Hat, I kind of feel that it's an important part of what we do. So I tried to come up with something succinct enough to fit into a 5-minute presentation. To that end, I'm going to go over our technique for leveraging IPython as benchmark driver, specifically to evaluate TLS performance. Now, why IPython? Well, if you don't know IPython is interactive Python that extends what you can do with the native Python shell. It was written for and by the academic community, and it has a lot of good scientific components to it. In addition, IPython Parallel brings us easy, convenient parallel computing. Why am I talking about TLS? Basically, just because it's a hot topic. Also, capacity planning is a big part of what I do, and there are some real justified concerns about enabling forward secrecy on devices that may not, or websites that may not already have it, particularly if you're scaling with hardware. So in this scenario, it's a lab test, and what I want to see is the particular rate at which we can, an endpoint can complete TLS handshakes given a consistent number of clients beating on it. Now I know that that's completely concocted, but just bear with me. The particular test driver that I'm using is a custom TLS handshake factory. It connects, it negotiates an encrypted session, and then it disconnects. For each handshake, it's going to return a whole bunch of timing data. And there's a little bit of information about the workers that I'm using, which live in AOL's private cloud. Okay, and here's, hopefully we can see this. Here's what the Python code to run it actually looks like. Okay, I set up the environment, I create the benchmark driver, and then I ask it to run a test. 60 seconds, 4 threads per worker. When I get my results back, I turn it into a panel, which is, in Pandas, a 3-dimensional array. So on the x-axis are the phases of the transaction, and the y-axis are the individual connections for the transaction, and the results per worker node are separated on the z-axis. I can actually look at this data granular to the thread in each worker, but that's a 4-dimensional array, and it's too early in the morning for that. So if you can see that, and you probably can't, you can see that I get back about 34,000 results per worker. Okay. That's hideous though, so here's a graph of it. In IPython, and these slides or these pictures are screenshots from an IPython notebook, it's as easy as calling the mean function on that panel and then telling IPython to plot it. So that's 2 lines of Python code and I get the result back. And immediately I have a visualization. And it tells me, hey, look, there's something weird because there's some banding. I can poke and prod a little bit more around in my data, and I can tell relatively quickly that half of my worker nodes are a couple of network hops away, so there's a little bit more latency on half of my workers. All right, not a thing. Here's the same test run with a different cipher suite. And really the only difference between this test and the previous one is that the asymmetric exchange mechanism is now ECDHE instead of RSA. Okay? And I run the same 60-second thread with 4 threads per worker, and you can see that I get back about 5,600 results per worker. And if I did my math correctly, 5,600 is less than 32,000. So let's visualize it here and take a look at the results. The scale kind of crushes the fact that we were seeing banding, and as we expect, the later phases of the transaction, where the math happens, are a lot slower on the ECDHE, and I should be showing them side by side, but I'm lazy, and nobody can probably see them anyway. So what does this result tell us? Well, it doesn't tell us anything interesting. It tells us that ECDHE is slower than RSA, and we know that. But the point is that you can see how trivial it is for me to generate this data. Just using IPython and a little bit of C code, I can easily roll a benchmark driver. I can easily do some ad hoc analysis. And this is really just the tip of the iceberg. If you're familiar with IPython, or if you haven't used it, it's an easy way to grab numeric data, crunch it, produce results. And since this is done in a notebook, I can save that notebook. I can send it to somebody else. They can reproduce the results. I can use other extensions like DEXE to output PDF reports that I can send back to my vendors, my developers, and say, here, look at all this graphical data. When they hand me an upgrade, I just hit go again, it reruns the same test, and I can compare results. But the point is that IPython is a great tool for doing this kind of thing. Questions? I came in right at 5 minutes. I thought it was way under.
Does Apple get any licensing fees for IPython?
Not to my knowledge, no. No? Okay.
John and ruin his reputation?
We have a little bit of time. I don't know if you guys have more questions for any of the speakers. We can do that. We don't need to do microphone and recording and all of this fancy thing. We can just continue having a conversation. Of course, yeah, we want to do that.
It's going to be better than someone karaokeing the one that remained.
Someone could ask a really good question. So, let's see if this works.
Hey, your Blueberry is back.
And as we learned, it's the other end of the table. Okay, so there we go. Okay.
Now it's all official. Yeah, it's all official. Sorry, it's
do
like
the Oprah thing.
There is no half-assed job.
Nana and I used to work together, so she knows I'm usually half-assed. So this is not going to be the most serious talk, but maybe there'll be some point to it. Okay, so 5 minutes. So postmortems. Who here does postmortems? Yay! Okay. So we do postmortems at Stack Exchange, and we wanted to get better at doing them. And if you think about any process, if there's some component of the process that happens every time, that's an opportunity to automate it or make it more efficient, and that's going to make things better. Now, if you do a time analysis of what it takes to put together a postmortem, there's gathering data and doing all these other things, and one of the common elements is finding who to blame, right? And that can take a lot of time, and or not, but it's not just the time, it's the fact that it can be disruptive to the team, because emotionally, from a psychological point of view, people really can't deal with a technical issue until they've gotten through the emotional issue. So the faster you get to blame, the faster you can actually work on the project. So we automated the blame selection. So all you do is you go into our chat room, each team has a chat room, and if someone says, "not my fault," oh, please work. Demos. I asked my coworkers not to say anything proprietary, so if you notice, they're talking about like, "Hey, what's the root password and stuff?" So if you say "not my fault," it picks everyone that's in chat in the company and randomly selects a person for blame. Now, the song that's being played right now, it's "I told you not to touch it, I told you not to touch it, I told you not to touch it, you broke it." And the choruses are about, "You did so well in the interview, but maybe now we need to reconsider." Oh, it picked Matt Sherman. Okay. So this has helped the team greatly.
Shut up and take my money.
I can't take credit for coming up with the concept or even implementing it, but I thought it was worth showing. But the real point is that postmortems should be blameless, and it should focus on taking responsibility and learning. And if you do your postmortems with a little bit of humor, it can break down barriers that were previously blocking communication and open people up to having a good, honest talk about the failure and how to fix things in the future. So, thank you.